The first law of thermodynamics, internal energy, heat, and work. Okay, so now we're going to talk a little bit more, quite a bit more actually, about the first law, but we're going to apply it to chemical reactions. And basically, we're going to look at the transfer of energy between that reaction and the surrounding area. Now keep in mind that thermodynamics is the study of energy transfers, essentially, and so thermo is heat, okay, and dynamics is change, so heat changes. Okay, so now this transfer of energy happens between what we call a system and the surroundings. And these energy transfers come in the form of work or heat. So the system itself is defined as the chemical reaction or whatever you're interested in. So we'll see a non-chemistry example in just a second. Okay, the surroundings are that part of the universe that the system can exchange energy or matter with. Okay, so the part of the universe that is interacting with that system. Okay, so how could we define these system and surroundings? Okay, so now let's use a non-chemistry example. So we have a fish in a fish bowl, and right now the fish bowl does not have a lid. Okay, so think about the different ways that you could define the system or the surroundings. Okay, so we said that the system is whatever you're interested in. So we can actually define this system in a few different ways, okay? So we could say that the system is the fish and the water, okay? Or we could say the system is just the fish, okay? And then this would be the surroundings. Or we could say that the fish and the water and the bowl, that's all the system, okay? And basically you define the system for whatever you want to study. So for whatever is convenient for what you want to study. And the things that are directly around, those are the surroundings. So they can exchange energy, they can exchange matter, and the surroundings are actually going to depend on how we define the system. So for instance, if we define the system as the fish, then the surroundings would include the fish bowl and the water. Okay? Now, we have two types of systems. They can be open or closed. Actually, there are more, but we're just going to talk about those two. Okay, so a closed system can't exchange mass with its surroundings, but it can exchange energy. Okay, so if we put an airtight lid temporarily on this fish bowl, then we would have a closed system. Now, an open system actually does exchange mass in addition to energy with its surroundings. So if we identify the system as the fish only, then the fish would eat and it would acquire oxygen and do whatever else fishes do in the fish bowl, and that it would be interacting directly with its surroundings and exchanging matter and everything. Okay? Okay, so let's go back to chemical reactions again, since that is our topic, okay? And we're going to be looking at this transfer of energy in terms of work, which is W, or heat, which is Q, okay? Now, this is the internal energy, okay? And you also might see delta E used instead of delta U, all right? And that's the change in internal energy of that system during a process, okay? Q is heat and W is work. Now, delta U or delta E is actually the difference in energy between the reactants and the products in a chemical reaction, okay? So the reactants are going to start out at some energy, the products will be at a different energy, and delta U is the difference. Now, delta U is actually the sum of all the kinetic and potential energies of all the particles in the system, okay? So basically, it's called the internal energy. It's basically the energy of that system. So we're adding together all the kinetic and potential energies, all the different kinds for all the particles in that system. And these guys can be exchanged by work, heat, or both, okay? So we can exchange that energy by work, heat, or both. Okay, so what's work? Now, work is the mechanical transfer of energy from one thing to another, okay? And heat is the energy transferred from a hot object to a cold one upon contact. Okay? And all of our energy transfers can be classified as either heat or work. We are going to focus on mechanical work in this presentation, and we'll discuss heat a lot more in later presentations. Okay, so here's a nice schematic that just gives you the signs of Q and W relative to what's going on with the system and the surroundings. Okay, so here we have a great big box, okay, and that we're going to call that the surroundings, okay, and then our system is inside this circle. All right, so there's our system. Now if we do work on the system, we put work in to the system, okay, we're doing work on it, then the sign of W is positive. Okay, if that system does some work, okay, if it does work, then the sign of W is negative. Okay, so we can determine whether work was done on the system or by the system just by the sign of W. Okay, and so when work is done on the system, that work is done by the surroundings. Okay, and when work is done by the system, it does work on the surroundings. Okay? Okay, so now same thing goes for heat. If we put heat into the system, okay, so if the system absorbs heat, then Q is positive, okay, and it's absorbing that heat from the surroundings. If the system releases heat, okay, so heat comes out, then that is negative Q. Okay, and that's heat released by the system to the surroundings. Okay, now remember that energy is conserved, okay? And there are some processes where delta U doesn't equal 0, all right? And basically if that happens, then that just means that energy must have been transferred into or out of the system in the form of heat or work. So it did go somewhere. It didn't disappear, all right? But delta U doesn't always have to be 0. Okay, so let's talk a little bit more about PV work, okay? And we're going to just talk about one very specific kind, and that's it, okay? And it's a mechanical transfer of energy from one thing to another. Now, in general, work is defined as a force multiplied by some displacement, okay? And the pressure is a force over a unit area. Here's an equation for work. This is actually the only one that we're going to use, okay? And so work is equal to the negative external pressure, okay? So that's the external pressure on the system multiplied by delta V, which is the change in volume of that system, okay? And the external pressure is the external pressure that the system expands against, okay? All right, so let's use that equation and calculate some work, okay? So how much work is required to compress a gas from 7.3 liters to 3.0 liters by exerting a constant pressure of 1.8 atmospheres? Think about whether we are doing work on the system or if the system is doing work. Okay, so first things first, are we doing work on the system? All right, so we're compressing a gas and we're using an external constant pressure of 1.8 atmospheres. So yes, so we are doing work on that gas. Okay, so the system isn't doing the work, we are doing work on it. And so if we use our equation for PV work, and we calculate our change in volume, okay? So we started off with 7.3 liters and we went to 3.0 liters, okay? Plug that in and we end up losing 4.3 liters. So the volume decreases 4.3 liters, okay? And then we have our external pressure, which is 1.8 atmospheres, okay? Plug those guys in and we end up with 7.74, And then we need to think about things because look at this. Look at those units. Liters times atmosphere. Okay. Now those aren't SI units. So we're going to have to convert those liter atmospheres to joules. Okay. And the conversion for that is 1 liter atmosphere is equal to 101.3 joules. Okay. So if we take our 7.74 liter atmosphere and multiply it by 101.3 joules, and see our liter atmospheres are going to cancel out, and we end up with 784 joules. Okay. Now again, going back up, looking at our problem, 2 sig figs, 2 sig figs, 2 sig figs, so it's unanimous. So we need 2 significant figures. This number is less than 5, so we're going to round that down to 780 joules. Now, the last thing to notice about this problem is that the sign of the work is positive. Okay, so this is positive 780 joules. Okay, and that was work that was done on the system. Okay, so finally, let's just introduce the concept of heat. We're going to talk about heat a lot more throughout this unit, but we just want to introduce and just talk about it a little bit right now. All right, so for exothermic reactions or processes, okay, exothermic releases heat, okay? The sign of Q is negative, so that's heat out for an exothermic reaction. So exothermic reactions release heat. These are the ones that generally feel hot, okay? Endothermic reactions or processes absorb heat, okay? And so these have a positive Q, okay? For an endothermic reaction, they absorb heat from the surroundings, and these are the processes that generally feel cool. So if you're holding something and it feels cold to you, that is an endothermic reaction, and that reaction is drawing heat out of you and into itself, so that it's absorbing heat. Okay, so what should you be able to do so far? All right, now you want to be able to use the first law and the equation for the internal energy, delta U, okay? You want to be able to define and or identify the system and the surroundings for various scenarios, all right? You also want to be able to describe and identify whether a system is open or closed, okay? Very important, you want to be able to tell by various words in the problem or the sign of W or whatever information you have. You want to figure out whether the system is doing work or having work done on it. You want to be able to calculate PV work for a given process, okay? And identify an exothermic or endothermic process using the sign of Q. So that's just so far.